Hello everyone, welcome back. So now we'll discuss module 4, that is differential amplifier design. Okay. So before going there, are you people able to see my screen and can you hear me?
Yes, we can see and
Yeah.
hear.
Yeah. Okay. So first question is, have you seen a differential amplifier? And before, yeah. So you might have studied in first year or second year in BTech, that is op-amp. So here the input is differential and output is single-ended. So the first stage of the input, that is nothing but a differential amplifier. So this is the typical representation, one of the architecture of differential amplifier. Okay, 5 transistor. So in any op-amp, the input, the first stage, that is differential input, will be a differential amplifier. So you can assume op-amp, it is nothing but a high gain differential amplifier. So the input stage is differential. To get the high gain, the CG stages will be cascaded to this differential amplifier. Okay. So op-amp is simply a high gain differential amplifier. And to get the better gain, the cascading or cascoding will be done in multiple stages. Okay. So in some cases, you will see output as a differential also. So the way input is differential, output can also be a differential output. Okay. And since the differential pair is at the input, so we will restrict our discussion to only the input side. Okay. So where all you will find this op-amp? So if you take into account of any band gap, LDO, or a V2I converter. So take any power supply block. So it will have a op-amp to regulate its output voltage, or to regulate the current, or to keep the two voltages exactly the same. So the op-amp is used. So it is used almost in every the power supply block. Okay. So if the op-amp is used, then the differential amplifier is used. So the diagram it is shown here is the NMOS differential amplifier. So similarly, they can be a PMOS differential amplifier where the input is connected to the PMOS diff pair. Okay. Yeah. So coming to single-ended and differential signals, so the here is the representation so of the single-ended. So any signal that is measured with respect to some common mode voltage. So this can be ground, or it can be some DC voltage. So if something is measured with respect to this DC voltage, then it is called single-ended. Where in case of differential, so we have two nodes, and both will vary equally and in opposite sign. It means when V out X increases, then V out Y is supposed to decrease. Okay, so it should be equal, and it should be in opposite directions. So this is the differential signal. Okay. And if you look at the input, so here, if you look at, this is the peak V out with respect to the DC. Um, so with respect to DC, it is varying. Yeah. So this is varying positive and this is minus negative. So the total peak to peak is 2V naught. Okay. But here it is varying V naught. Here also it is varying minus V naught. But Here again it is varying minus V naught and V naught. So at this point, if you take the difference, it is 2 V naught, and here also it is minus 2 V naught. So the overall, the peak to peak we get is 4 V naught. So it means the swing what we get from the single-handed is 2 V naught, and it is differential is 4 V naught. So the swing is double in case of differential signals. Okay. So any questions on this? Yeah. So please note here the differential assumption is the signals varies equally and in opposite direction. Okay. So let's say this is grounded and this is varying, then it is not a pure differential signal. Okay. So it has both the components, differential and the common mode. Okay. So as per the definition, both should vary equally and it should vary in opposite direction. Okay. So question is why differential signal? So here is the one diagram which tells what could happen with the single dead and what could happen with the differential signal. Okay, so if you look at any IC, so there will be lot of blocks. There can be a switching block, it can be a clock generator, and there can be a digital circuit. So it does the processing. So all clock and everything is routed. And here can be a power supply unit, PMU. This could include band gap, or this can have a LDO, or it can have a PLN. It can be anything. So like that, it is placed somewhere here, and this clock might be routed close to the PMU unit. Okay, and this is the one such diagram. So this is the CS stage. Its output, it is analog in nature. So that is routed to some other block. Okay, and here the clock is going. So the clock will be continuously switching. Okay. So these two lines are routed very close to each other. Okay. So in such a cases, there is a parasitic cap. So this is coming because of the parasitic. So everywhere there will be a parasitic cap. Okay. Sometimes what could happen is the supply voltage also will carry some noise. So that might also be routed very close to its output. Okay. Somewhere here. Okay. So that will also have some capacitor. Okay. Routing capacitance. So what happens on clock jumps? So through this capacitor, even L1 signal will vary. So because of that, there is a crosstalk or coupling of this clock on this voltage. So hence the output will have some spikes, something like this. So there can be some overshoot and some can be undershoot like this at every rising edge and falling edges. So this is what it happens. But if it is a differential signal, so in case of differential signal, we look at the difference L2 minus L3 voltage. Okay. So the coupling, what it does, the overshoot and undershoot, it is almost equal if these capacitors are matched properly. So the spikes you see on L2 and L3 are equal. So if you take the difference, because it's a differential signal, so if you take the difference, then you will not see these spikes. So it will be cancelled out. Okay. So that is the advantage. So any digital signal or any noisy signal, if it is routing very close to the differential signal, then the noise, the common mode noise will definitely increase. So the common mode noise will definitely there, it will increase, but the differential noise will be, it will be like nothing. It will not have any contribution. It will be cancelled out. But if you look at here in single-ended, so the noise which comes, okay, that is getting added directly. but here you can see here it is added on both the lines. Because of that it will cancel out, so finally we get a voltage which is the signal voltage. Okay, got it. So that's why differential signals are preferred over the single ended. So if you take any sensors, for example, it can be ECG, or it can be a heartbeat sensor, or any sensors. Okay, so it's the actual signal strength will be of the order of microvolt. Okay, so but the noise what we have during the routing and during sensing and transmission, so that noise will be much more than this microvolts. So what happens there, so differential signal is transmitted. So because of that, all the noise will appear on the both the lines. Okay. So when you look at the difference, you will see the proper the signals. Okay. So for any sensor whose output sensitivity is very important and it is signal strength is very small, of the order of microvolt, then the differential, taking it as a differential is will improve the noise immunity. Okay. Okay, so any questions on this, guys? Okay, so if no questions, then we'll move to the next slide. Yeah. So here one more example it is shown here. So the supply will also have a lot of noise. So this is because the same supply could power the clock generator or the oscillator. Clock oscillator it can power. Okay, and the same supply, if it is connected to the IO ports, then IO ports usually take a few milliampere of current. So every time it takes few milliampere of current, then VDD will dip. So in that sense, since it is connected to many other sub blocks, it will carry lot of noise. Okay. So if the VDD changes, if VDD changes, so it depends on power supply rejection. Okay. So this could directly affect the V out. Correct. So if VDD changes, then V out level will automatically change, because this, if you assume this is current is constant, because VGS is fixed here. So any VDD increase will definitely increase the V out, because I here is fixed. Okay. So, but if you consider the differential configuration, so any change in VDD will change both the Vx, and also it will change the Vbot. So since the common mode voltages are increased, but if you look at the difference, there is no change in the difference. Okay. So it means that differential signals will have a very good immunity towards the supply noise. So this is one more reason why differential signals are better than the single-ended signals. Okay. So this is the advantages and disadvantages of differential signals or differential configuration. Okay. So here the common mode noise rejection is much better. So since the noise is coupled to both the terminals, so the differential will not have this noise content. Okay. And second one is it simplifies the biasing. So this we will discuss in the next slide, how it simplifies the biasing. Okay. And the third point is a larger maximum signal swing. So we have seen for single-ended it is 2 V naught, for differential it is 4 V naught. So this is for the single-ended. Okay. So because of this, the swing is 2x times better than a single-ended signal. Okay. And coming to linearity, so linearity in the sense, there are two things. One is homogeneity and superposition. Okay, and superposition. Okay. So any signals which satisfies these two, then it is called linear. Okay. So here, in case of differential, it is more linear. Might be we will discuss more in detail, but one few reasons to justify is you can look at the noise, the supply noise. Okay. So when supply noise is applied, okay, then so whatever the V out we get, so that will be the sum of supply noise and the input signal. But in case of differential, the it will come as a common mode. Because of that, it will cancel out. Okay, got it. So there is no amplification. So in that way, the homogeneity and the superposition will be met. Okay, so this is the one. Okay. And if you look at the circuit point of view, so this is the one simple example where CS amplifier is there. Okay, so we discussed. Okay, CS amplifier. So this is the single-ended input and the single-ended output. Okay, okay. So when V changes, it changes the VGS. Okay, and if the V changes a lot, then we have a curve something like this. Okay. So if the Vin changes in large signal, then the GM what we get at this point, it is different than this point. So the GM1 is different than GM2. So at this, it is GM1, and at this point, it is GM2. Okay. So it is different because of that the common mode voltage, if it is increases, okay, we get a different GM. So you can conclude, let's say you are giving common mode voltage 1 at, let's say, 0.5 volt, and one more you are giving common mode voltage at, let's say, 0.8 volt. Okay. So at 0.5 volt, GM1 is different. At 0.8 volt, GM1, it will change to GM2. So it is different. So we are getting the different GM. So because of that, the gain what we get from this CS amplifier is different, and it depends on V common mode voltage. So when V common mode voltage is changing or increasing, then GM will also increase or it will change. Because of that, the gain is changing. So it will not satisfy the superposition theorem or homogeneity. Okay, because at a different common mode, it is behaving in a different manner. Okay, but in case of differential, so you have a differential input. Okay, so when V common mode is 0.9 volt, okay, so what happens is the source node will get adjusted. Let's say the VGS is 0.3 volt. So the source node itself will get adjusted to 0.6 volt, and VGS will remain same, that is 0.3. Okay. So when 0.9 or 0.9 reduces to, let's say, 0.5 volt, so both are reducing to 0.5 volt. So this 0.3 will remain as it is, and the source node voltage will reduce to point, how much it is, 0.2 volt. Okay, so but VGS is exactly the same. So in that way, so this kind of the operating point movement will not happen. So the VGS is fixed exactly at around 0.3 volt or 0.4 volt. Okay, so because of this, the differential circuits will have a better linearity compared to the single-ended circuits or the signals. Okay. And coming to the disadvantages, the double the area, because in single-ended you need to have a single CS amplifier, but in differential you need to have a CS amplifiers. Okay, so the area is double and the power is double because both has to carry the current. So the current increases, the power increases. So these are the two disadvantages, but so we have seen the problem with the CS amplifier, that is the common mode voltage. That is setting based on this the common mode voltage, all the parameters will change in case of CS amplifier. So even if it changes by 30-40 millivolt, so the entire operating point will be changed. So this is the big problem with the single stage amplifiers, setting the operating point. So, so the only option we have is the differential amplifiers, so which will take care of this bias by rejecting the common mode voltage. So this is the one example which explains how it rejects the common mode change. Okay, so so differential amplifier is something which is used everywhere because of the advantages it offers. Okay. So, okay, so any questions on this, guys?
No, sir.
Okay, so we'll move to next. So question is how to convert a single-ended to differential. So that this is one simple way of doing it. You have a transformer where input is connected to the single-ended input. So this will divide into half, positive and negative direction. So the common mode, this is the common mode terminal of the output. Okay, so if you change this node voltage, the output will swing with this reference voltage. Okay, it can be grounded or it can be connected to common mode. So when it is connected to common mode, so the both terminals will have a common mode voltage. So on top of this, the signal will vary. Okay, yeah. So we have a differential amplifier. So question is how to define the differential input and common mode input. So we have two inputs, V in 1 and V in 2. Okay. So I'm going to define a differential signal, that is Vd as V in 1 minus V in 2. Okay, so this is the differential signal, whereas common mode, I'm going to define it as a V in 1 plus V in 2 by 2. Okay, so this is the definition. So we have seen the differential signal is the signal which varies equal and opposite direction. For example, if this increases with the same magnitude, V2 should reduce. Okay. So so this out of this difference, the half is given here. So it increases by half, Vd by 2, and this reduces by half minus Vd by 2. So that's what it is written here. So the difference divided by 2, so it increases and this will reduce. So V in 2 minus V in 1. Okay. And common mode. So this is the V common mode. And this is the V differential by 2. Okay. So when you combine both, okay. So when you combine both, this will cancel out. This will cancel out. So finally, you will get V in here, V in 1. So V in 1 is nothing but Vd by 2 plus V common mode. Okay. And similarly, V in 2 is minus Vd by 2 plus V common mode. So this is the differential component and this is the common mode voltage. This is the differential and this is the common mode. So it is differential is varying in equal quantity and in opposite direction. That's why it is negative coming here. Whereas V common mode is common to both input. Okay. Yeah. So here you can look at the V common mode voltage. Okay. So it is exactly the same. So you can short it. So after shorting, you will get something like this. So here VD by 2 is connected. Here minus VD by 2 is connected. Okay. And this is the common mode voltage. Yeah. So any questions on this? So this diagram is exactly the same one. It is split into different components. So there is, yeah.
Common mode will be like biasing voltage only, right?
So when you combine all this, it is exactly the V in 1 and V in 2. So the only you are representing V in 1 as a common mode and differential. That is V in 1 is V common mode plus V differential by 2. And similarly, V in 2 is common mode minus VD by 2. Okay.
Okay. So
So did I
it
answer your question?
so here also it's looking like that VCM will be like biasing, and VD by 2 will be the differential voltage going to that
Correct. Correct. Yes, yes. This basically comes from biasing itself. And this is the signal frequency. Sorry, signal amplitude.
Okay, good.
Okay. So this is how you can separate. So differential is defined as a difference between V in and V in 1 and V in 2. And yeah, so at the input side, you are giving half of the differential signal, and on the other terminal, it is giving you are giving minus half of the differential signal. And V common is sum of these two by 2. Okay. Yeah. So this is the one pseudo differential amplifier. So here the input, these are nothing but two CS stages. So the V in 1 is connected to one CS stage and V in 2 is connected to another CS stage. Okay. So here V out 1 and V out 2. So the differential output will be equal to V out 1 minus V out 2. So this is where we are interested in. Okay. So when V in 1, let's say it is at the supply. So when V in 1 is at the supply and V in 2 is at the ground. So this is too high and this is too low. So when this is too high, then V out 1 becomes 0 because this is completely on. So it will pull the V out 1 to ground. Okay. So in this case, the V out 1 will be 0 volt approximately. Okay. And V out 2 will be, so this is very small of the order of 0. Then this is off. If this is off, then no current flows through M2. So the V out 2 will be pulled to supply voltage through RD. So V out 2 will be VDD. Okay. So if you take the difference VD out, it will be minus VDD. Okay. Similarly, when V in 1 is 0 and V in 2 is supply, then V out 1 will be VDD and V out 2 will be ground. So the differential output is plus VDD. Okay. So I am assuming this VD sat is very like ideal component. So VD sat is very small, or else this can be a VD sat, you can assume. Okay. And this also you can take it as a VD sat in practical circuits. Okay. So this is a large signal input and output swings. Okay. So we will look at the small signal in the next slides. Okay. Yeah. So this is the small signal. Here input is differential VD by 2 and the V into is minus VD by 2. Okay. So if you take the first stage, so this is nothing but the CS stage gain equation. So that is minus GMRD into the input signal. Here input is VID by 2. So this is where input is given VID by 2 differential. Here it is minus VID by 2. Okay. So the output node voltage due to the first one input is this one. This is the output. Similarly, the output V out 2 due to V in 2 is this one. This is the gain into the input signal. Okay. So, but we are interested in the difference. That is, we want the differential output. So that's why V out minus V out 2. So this is the differential output voltage. So if you combine, this is minus GMRD into VID. So this is nothing but the gain of CS stage multiplied by the differential input. Okay. So this is the term, this is the gain term, and this is the differential gain. That is the differential output divided by differential input. So that is still minus GMRD. So this is exactly same as that of CS stage in case of single-ended signal. Okay. And if you look at the, it is nothing but a single-ended CS stage. So here also gain is same. And the second stage, that is negative terminal which is connected. So here also it is a CS stage. It is gain also exactly the same. Okay. So the differential gain, it is coming same as that of single-ended CS stage gain. So any questions on this? Okay. Yeah. So now we have looked at single differential small signal. Now we will look at the common mode small signal. So in common mode, the input, it is connected to V common mode, and similarly V in 2 is also connected to V in common mode. So this is V in, okay, so this is V in common mode and V in common. So here both voltages will increase at the same time with the same magnitude, and both will reduce. So there is no opposite sign here in case of common mode. So either it will increase equally or it will reduce equally. Okay. So that's why there is no negative here. It's purely plus sign. Okay. And coming to V out one, this is the CS stage gain. So this is the CS stage gain, and that will be multiplied with the input. Okay. Similarly, V out 2, again, this is the CS stage gain multiplied with input. Okay. And so the V out common mode, it is defined as V out 1 plus V out 2 by 2. So this is the definition. So here you can see the even the common mode signal is getting amplified, and the gain is same as that of CS stage. Okay. So if you take the common mode gain, uh, the ratio, so we get it is same as that of CS stage gain. Okay. So this is a common mode rejection ratio. So this is the one parameter. So AD by A is common mode. So the differential gain and common mode gains are same in this configuration. That's why it is 1. Okay. So this parameter has to be very small in the sense the differential gain has to be, sorry, it should be high. It means it should be high, and the common mode gain should be low. So this is because the our information is in the differential signal, that is the difference V in 1 minus V in 2. So this is where our information is present. But common mode is just a DC biasing. Okay. So if the common mode is changing, then even in this case, the V out is changing. Okay. So this is the problem with this circuit. So if the DC bias is increasing, then so V out should not change. It should not get amplified. Okay. So this is the common mode small signal analysis of this pseudo differential pair. Okay. So this way have already seen the large signal. So so when V in 1 increases, then this NMOS will turn on. So this will pull the V out 1 to ground. Okay. So similarly, when V into okay. Similarly, in case of common mode, this will increase in the same direction. Okay. So this will increase in common mode. Even this will increase. Okay. So if both increases, then V out 1 and V out 2 both will reduce because current increases through these MOSFETs. Okay. If current increases, then it will pull this node to ground because the drop here increases. Okay. Yeah. So they are in phase. So the maximum current that flows here is VDD by RD. So I'm ignoring VD sat. So this is the VD sat I'm ignoring. Yeah. So this is the maximum current it can take. So in differential stage, we saw if this increases, then this will reduce. Because of that, one will be pulled to supply, another will be pulled to ground. But in case of common mode, so both will be pulled to ground or it will be pulled to supply voltage. Okay. And we have an equation. So that is ID is equal to GM times of VGS. So this is the small signal equation where the input signal, it is linearly related to the output using this term. This is a small signal. But if you would like to calculate the large signal, then you should use this equation, that is ID equal to mu n Cox W by 2L. So VGS minus VT. So here this is the input and this is the current. So it is square term. So it follows the square law. That's why it is called, it follows the square law. Okay. For small signal, this is the equation. For large signal, this is the equation you should follow. Provided it is in saturation. Again, if it is in triode, then one more equation will come. Okay. Okay. Yeah. So the two stages acts like two independent CS amplifiers. So these are the CS amplifiers. Okay. And the transistors are biased by the input common mode level. So this is the main problem with this stage. So the input itself biases these two MOSFETs. Okay. And if the common mode increases, then current increases and even V out changes. So this is another one problem. So the operating point is sensitive to the input common mode level. Okay. And if the V common mode increases, we have seen the both voltages will increase, V in 1 and V in 2. so which will result in increase in the currents ID1 and ID2 current through these two MOSFETs. Okay, and if it is a large signal, then you should use the ID equation which has the square of VGS. Okay, so once Vin increases, then Vout will reduce. It will crush the VDS of this MOSFET, and in worst case, this can go to ground, and the current in that case is VDD by RD. Okay. Yeah. Going to next. So this we have seen. So the CS stage, two CS stages has lot of problems. Okay. So it depends on the input common mode. So output changes with the input. Its operating point completely depends on the input common mode. Okay. So it has lot of problems. Okay. So to make it more better, so one thing we can do is using one more CS stage. Okay. So we have a source degeneration circuit. Okay. So now this is V in 1 and this is V in 2. So both are connected to supply. Here RD is exactly, it has to be same, and here RS needs to be exactly same. Okay. See, this source degeneration circuit we have seen, that is the gain is nothing but RD by RS. Okay, and the Vin supposed to be selected such that the current should be decided by this RS. Okay, so the current through the MOSFET ID1 is nothing but V in 1 minus of VGS divided by RS. Okay, so here V in 1 of VGS you can split into two things, that is VTH plus overdrive voltage. Okay, and this is RS. So in our example, we have seen V in as a 2 volt and the VTH is around 400 or 450 millivolt. Okay, so we have chosen this very small 100 millivolt. Okay, so if the current varies a lot, then the overdrive voltage uh, it changes very small, correct? Because this is 100 milli, even if you add 50 milli, so compared to 2 volt, this is very small. Okay, so in that way, you can approximate it like V in 1 minus VTH by RS. Okay, so V in is input, okay, and VTH is the threshold, it is also constant, and this is the RS, it is also constant. So the current mostly depends on RS here. Okay, so in case of common mode, so let's say you are connecting this to V common mode, and this is also exactly the same V common mode. Okay, so you have a source voltage here and here, so both are exactly at the same voltage. Okay, so V common mode, and here you are connecting to V common mode. So when V common mode increases, okay, the source terminal will increase, so this will increase, both will increase. Okay, so since the two MOSFETs are identical and RD is identical, exactly the same, and here RS is identical, so these two node voltages are exactly the same. Okay, so what I'm going to do is I'm going to short it. Okay, so when you short this drain terminals, so what will be the ID current here, or the current that is flowing through these two terminals?
0.
0. Yeah. So this is because this is exactly at the same voltage. So this is also exactly at the same voltage. So the current here is 0. So it is kind of open circuit. Okay. So if you represent the same circuit here, so you have RD. So you have RD. So both are connected to VDD. Okay. So both are connected in parallel. So this will be what? RS by 2. Correct. Okay. So now both are connected to V common mode. Okay. This makes sense. So you can make out RS by 2. Why it is RS by 2? For one more way of doing the interpretation is, let's say here it is pushing some I1 current. Okay. This MOS is pushing some I1 current, M1, and this M2 is again pushing some same current, I current, because both are identical circuits. So this is I and this is I. So here here also it has to be exactly the same. This is I, this is I. So the I total should be sum of these two. So that is 2 times of I. But for the representation, we should have exactly the same voltages here, this point and this point, because these two are identical circuits. Okay, this has to be exactly the same. So that will happen when you reduce the resistance. So this source voltage and this source voltage exactly the same. That will happen when you reduce the resistance by half, so that the 2I will flow through this resistance. So 2 will cancel out and it will give you the voltage. It is exactly same as that of this voltage. Okay. Okay. So this is the one. So the next one is, let's say V common mode increases. Okay. So when V common mode and this V common both has to increase at the same time, both increases, then Vs will increase. Correct? Okay. If Vs increases, what happens? So the current flowing through this one, the resistor is Vs by Rs by 2. So this is constant. So the current will also increase. Here current is increasing. Make sense? Okay. Yeah. So there is okay, let me change it. Okay. Okay. So this delta change, let's say it changes by delta VCM. Okay. That is causing delta change in the source voltage. Okay. So the change in current is delta V common mode divided by Rs by 2. So this one I will represent it as Rs dash. Okay. So delta V common mode, it is Rs dash. So this is the change in current due to the change in common mode. Okay. So the same current, so it is equally divided between these two. Correct. So the same current will get added here. Sorry. So, so the same current, it is getting added I by 2 here. And similarly here earlier it was I. Now it is getting added delta I by 2. Okay. So this is the current by 2 by 2. And so that is flowing through this RD. So the change in V out is what? Change in V out 1 is nothing but RD into change in current due to the common mode change. So that is nothing but RD into, you can substitute exactly the same, delta V common mode divided by Rs dash, and 2 will come here. because this is I by 2, that is delta I by 2 here. Okay, delta I by 2, delta I. Got it? Yeah. So this becomes RD into delta change in common mode. So R dash we can substitute. So this will be, it will cancel out. Finally, we get RS. Okay. So now what happens? The change in V out due to change in V common mode is nothing but RD by RS. So this is the gain equation. Okay. So the common mode gain is nothing but RD by RS. Okay. So you need to note here, this is RS. So we are comparing it with the CS amplifier. Okay. But if you look at this circuit, if you see only this circuit, then this common mode equation will change. So it will be what, RD divided by 2 times of RS dash. So this is the equation. So I am substituting RS dash, that is, this is the resistance, just a representation. If this is the case, then 2 will come here. Okay. Got the point? So it means, so let's say RD and RS are same. I'm choosing RD. Earlier for gain 2, we have chosen RD equal to 2 times of RS, approximately, or more than 2 times of RS. Okay. So in that case, what happens if you substitute here? So the common mode gain will be approximately RD is 2 times of RS, and this is RS. Okay. So it will be 2. So it will be amplified by 2 common mode gain. Okay. So let's move into how to improvise it. So we have seen RD is coming here. I mean, RS is coming here. So if you increase the RS here, if you increase this resistance, then we are going to increase the reduce the common mode gain. Okay. So how to do that? That you can do it with the current source. So so now we have seen the common mode gain as RD by the 2 times of resistance seen here, uh, 2 times of RS dash. Okay. So for the current source, the resistance is, so for current source, so the resistance is infinity. Okay. So what happens? Common mode is RD by infinity is nothing but 0. Okay. So it means when Vin increases, okay, Vin increases, okay, so the source node voltage will increase, okay, but this increase in Vs node voltage, okay, will not change the current. It is fixed. Okay, this is fixed. Since it is fixed, these currents are fixed. So this is also fixed. So what is the V out? V out will stay as it is. So V out will be I into RD, or I by 2 into RD. So it will not change. Okay. So that's why we connect here a accurate or high impedance current source. So ideally, its impedance needs to be infinity. So to reject all uh, the common mode.
Common mode gain.
Yeah. Okay. So we know already. You can connect one current source. So maybe we will discuss in the next session. So you have a you connect a VB voltage, some bias voltage. So if you look at from the drain, the R out you see is RDS or R naught. Okay. So if you make it cascade, then you will see it GM R naught square. Okay. So R out can be in terms of few mega ohm. Okay. So this can be a few hundreds of mega ohm. Okay. So you can substitute here. In many cases, so this RD will be again a current, again active load. Active load in the sense it's a current mirror. So its resistance will be RT. Okay. So in this case, the common mode gain is again RD divided by here also it is RD, 2 times of RD. So it will cancel out the common mode gain could be 1 by 2. Okay. So if you make it a PMOS active load, and this is also PMOS active load, then the common mode rejection will be of the order of this number. Okay. So you need to make this a cascade to get the better rejection. Okay. See, one more way of doing the interpretation here is, so you have a NMOS. So again, this is a current mirror. Okay. So here, this node voltage is connected to here. Okay. So this node voltage is changing. Okay. So you have a curve. So this is ID and VDS. So basically, we are changing the points here at this point and at this point. Okay. So if this is more flat, something like this, then R out will be higher. Okay. So when drain to source, when voltage changes, okay, the current changes. So this is a change in current. Okay. So this change in the current due to the smaller R out. Okay. So it will reflect at the output. It okay. So the output will be the change in this curve, the small change in this curve. Okay. That is divided equally. That's why it is delta I by 2 into RD. So this is the change in the output due to the change in current. Okay. Okay. So this is how we got a differential amplifier. So you can see here. So it's a symmetric circuits. Okay. So by even if you connect it, current will not flow. That's why it is virtually the same voltage. And please note it is for the common mode input, not for the differential input. Okay. So all the analysis is done for the common mode input. So for this circuit, this is exactly at the same potential. That's why you can short it. So when you short it, the resistance becomes half. Okay. And so even this is not sufficient, because when the input increases, the source node voltage will increase. So since it has a finite resistance, the current will also increase. So how to make infinite resistance? Basically to keep the current constant irrespective of change in Vs, that is by using the current source. So if you use the current source, then even if the VDS, that is the voltage across this current source changes, the current will not change. It will be constant. So if you have an ideal current source with the resistance of infinity, then the common mode gain will be 0. Okay. Okay. So let's go to the PPT. Okay. Yeah. So this is how you come across this current source, and this is nothing but a CS stage only. So instead of connecting resistance, it is shorted here with the current source. Okay. So we will do the differential small signal and common mode small signal uh, analysis of this differential pair, and also we will look at the large signal, both common mode and differential signals. Okay. So the same principle which we discussed, it can be explained in one more way. So this is the one simple circuit. So it is symmetric. So here R1 is exactly equal to this R1, and R2 is common to both circuits. So it is perfectly symmetric. Okay. So so for the differential signals, okay, here differential signal is applied. Okay. And when this increases, then other signal is reduced. Okay. So when this increases, it is basically pushing some extra current. Okay. And at the same time, this is reducing with the same magnitude. It means it is pulling some current from the same node. So the current which is pushed here, it is drawn from another terminal. Okay. So the current that is flown in R2, nothing got changed. So all the current which is coming here, it is pushing to the other side. Okay. So there is no change in the voltage across this R2. So because of that, you can say that the change in current through R2 is 0. That will happen only when the other terminal is ground. And please note, it is a AC ground. So I am talking only about the changes. So if delta change happens here, okay, it will push some, let's say, okay. So let's say it is changing by delta V. So the current here is delta V by R1. Okay. And this one is changing in minus delta V in opposite direction. So the current will reduce. So the current will be in this direction, that is delta V by R1, the equal amount. So all the current that is pushed here, it is drawn from this terminal. So what is the current that is flowing here? It is 0. And please note, it is a delta I current. Okay. So this is delta I that is given, and this is also delta I which is drawn. Okay. So this is 0. It indicates it's ground for small signal, virtually ground. So this is the advantage. So take any circuits which is symmetric. So the first point has to be perfectly symmetric. This is first key point. And second key point is this one, differential signals. It is only for the differential signals, I'm assuming. Okay. So this is the second key point. So if these two conditions are met, then we can say the components which are present in the vertical uh, at the symmetry of this axis. So here it is virtually ground. It will not consume any current. Okay. So any questions on this?
No, sir.
Okay. So now we know that this is virtually ground. Okay. So it means that I can write it something like R2 is not taking any current. So I can split it into two parts. Okay. So let's see what happens. Okay. So this is what it is. So R2 is split into two parts now, R2 and R2. So even if I connect here, the current is zero. I mean, the current that is flowing here, it is zero. Okay. So you can, because of this, you can analyze it independently. Okay. So this is the one. So coming to common mode. So let's now look at the common mode voltage. Okay. So in common mode, what happens is the delta V. I will take one more marker. Okay. Yeah. So this is the delta V if it increases. So this is the common mode. So this also has to increase in the same direction. Okay. So this is what the common mode is. Okay. So when common mode both are increases, okay, in the same direction. Okay. So this node will also increase. Correct. Or is it remain same? So when both voltages are increases, what happens to this node voltage?
Both will change, then this also will change, right? In the same direction they are changing.
Yeah. So this is the delta V. So the current will be this one. It is pushed in this direction. Similarly, this is also pushed in the same direction. That is delta V by R1. Okay, this voltage will increase by same amount. Got it? So this you can relate it to what we discussed earlier. Yeah. So when V both common mode voltages here increases, the source node will also increase. Okay. So this is for the common mode. So for the differential, okay. So if the V in one increases and this decreases by same amount. So when V in increases, this current will increase. Okay. And this current will reduce because this is reducing. This is a differential signal. So this, the total current it is coming here, it is constant. So this increases and this reduces, but voltage here remains exactly the same. Okay. So this is virtually ground. Okay. So for common mode signals, for a differential signal, so this acts like a virtually ground. And if you look at the symmetric circuits, this will also act like a virtual ground. Okay. But in common mode, this node voltage will be pulled to up. Similarly here, it will be pulled to up. Okay, that is the point. So the same is explained here. Okay, yeah. So coming to a differential stage, the small signal analysis. Okay, so we can use the half circuit principle. Okay, here V in one and V in two. So V in one is VID by two, but V in two is negative VID by two. It means that V in one, if it is increases, this has to reduce by equal amounts. So that's how the definition of a differential signal is. Okay. Yeah. So we have seen here in the previous slide. Okay. So if this increases and this reduces, then this remains exactly like a virtually ground. So this voltage will not change because increase in VGS it is compensated by increase in current. So since here VGS is reduced, this current reduces. So the overall sum is exactly the same. So this is ground, virtual ground. Okay. So this point is ground. So VP virtually it is at ground. So if it is ground, this acts like a pure CS stage, and this is also acts like a pure CS stage. So V out one is the CS stage gain, GM of this M1 into RD. Okay. And into the input signal. Here input signal is half of VD by 2, VID by 2. Okay. Same for second one. So this is V out 2, and so this is negative because it is a CS amplifier. Here also it is negative because of CS amplifier. Okay. So this negative sign coming because of the definition of the differential signal. Okay. So both will cancel out. Okay. So the differential output is change between the V out 1 and V out 2. So if you take the difference, it will be GMRD into VID. Okay. So these two basically it is V out 2. So this has to be here it is 2 and this is cancel. These two come here. Okay. So this minus GMRD into VID. So if you take the ratio, then you will get the gain which is same as that of CS amplifier. Okay. So if you take the individual gains, then also it is the same, that is GMRD. Okay. So this is the differential gain. So the differential gain is now it is clear. It is GM of this NMOS into RD. So it depends on polarity in what direction you are taking. So you have two outputs. So whichever, if it is, this is a 180-degree phase shift. If you apply here VD by 2 and minus VD by 2. So here to here, this is a 180-degree phase shift. Okay, here to here again, this 180-degree phase shift. So it depends on the polarity. So either it can be minus GMRD or it can be plus. Okay. So for the differential input, this is virtual ground. So the entire circuit will be simplified because of that. Okay. Yeah, this is what it is. So coming to the common mode gain. Okay. So this is something you can do it as a homework. So you can use the superposition theorem. Okay. So we did RD divided by the resistance. Okay. As the common mode gain. So we approximated it actually. So this is RD divided by uh, RS dash. So this is the one we did. But if you look at the resistance here, so this will be 1 by GM. So actually it is RD divided by 1 by GM plus of RS dash. Okay. So this 1 by GM factor is still here. So in case of common mode, uh, you can separate out. So this becomes one current source, but the resistance seen here will come. So you have a 1 by GM resistance here. Okay. Now the common mode gain of this first stage will change. So it is RD divided by 1 by GM. So the gain is GMRD. So I'm doing the superposition theorem. So considering V in 1. So this is the gain. The output here is V out 1 and input is VI1. Similarly here for this stage, the resistance in here is 1 by GM. So again here gain will be RD by 1 by GM. So that is GMRD is the gain. So this is for V out 2 by V in 2. Okay. So this is what it is. Okay. So this is the procedure you need to follow and use the superposition theorem to calculate the common mode gain and also the differential gain of this circuit. Okay. So so in earlier case we have looked at the symmetric circuits. Okay. So we assume this is a ground. Because of that, the gain will be GMRD. Okay. So with this method, you are not going to use this concept that is virtual ground. So instead, you are going to uh, solve using the superposition one by one. Okay.
Okay, sir.
Yeah. So see the symmetric method, that is assuming VP ground. So that's how we concluded using the symmetric circuits. So that is applicable only when M1 is equal to M2. That is, the W by L ratios are exactly the same, and RD of this supposed to be equal to RD of this. Okay, it has to be exactly the same. But let's say if I am taking 2W by L here, so then it's not a symmetric circuit. Okay. So then how to calculate the common mode gain and differential gains? Okay, so that you can do using the same method here that is listed using the superposition theorem. Okay, so if you use the superposition theorem, so for V in 1, so this is the V in 1.
We'll try this one.
Yeah. Okay. So this is the example which I quoted. So here the width is different for these two masses. Because of that, these two masses are different. So it is not a symmetric circuit at all. So you cannot use this ground virtual ground concept. You need to solve using the superposition by applying V in 1 first and then applying V in 2 next. Okay. You can try the method even here. Sometimes this way of sizing is done in LDOs, mainly to improve the offset. Okay. So you can identify how much change increasing this width will reflect at the output. Okay. So this is something you can do it. It is good activity. Okay. So the previous one, this exercise, do it even for uh, this circuit. Okay.
Okay, sir.
And yeah. So the half circuit principle is applied here. Okay. So because of that, this PP will be exactly at the same voltages. Okay. And when V in 1 increases and V in 2 increases, so the VP will increase automatically because of current source is connected here. There is no change in current. So this is the case in case of common mode input. Okay. If both voltages are increased, VP will increase, and increase in VP will not cause any change in current. So output change in output will be 0. So that's what it is written here. So change in output is 0, and here it is true even in case of V out 2. So the change in output is again 0. So we get a common mode gain which is 0. So the common mode rejection ratio, it is infinity. So this is the common mode rejection ratio, that is the differential gain divided by common mode gain. So AD by 0 is infinity. Okay. So the common mode is not sensitive to the common mode input. So the common mode output, so that is possible because of the current source having a resistance of infinity. Okay. So that's how the common mode input is completely rejected. So this is the main advantage. If you compare it with a single stage amplifier, okay, so for even 10 millivolts change in input voltage, the output was changing a lot. So now if you have a ideal current source, and because of the symmetry principle of half symmetry, so the entire common mode input it will get rejected. So it doesn't matter at what voltage it is at. It can be biased at 0.6 volt, it can be biased at 0.9 volt or 1 volt, it can be anything. So just you need to make sure all are in saturation. Okay, so this M1 and M2 needs to be in saturation, and if this is the current source, then it should work like a current source. It means if it, most of the times it will be a active current mirror. So this MOS also needs to be in saturation. Okay, so differential amplifier is independent of the common mode voltage, provided the current source has the infinite current, the output resistance. Okay, so this is the method two. Again, I think this is the homework, so you can look at this problem statement and uh, yeah, come up with the differential gain and common mode gain for these circuits, so without using the half symmetry principle. Okay, the same thing is explained here. So you have a CS stage with the source degeneration resistance. So the advantage of this resistance is the current flowing here becomes independent of V in, and it so in the sense it's not completely independent. So the current will be V in by RS. So it is a linear function, V in by RS. So this is the advantage. Okay. So it depends on V in, but it is linearly depends on V in. Similarly here, so when you short it, the current flowing between these two still it is 0, because both are at the same potential. So this is what it is. So if you short, then the resistance becomes half. So this is RS. So here earlier we took this as RSS. Because of that we got this RSS by 2. Okay, so that is the difference. Okay, yeah. So we have this is nothing but a common gate amplifier gain. We have already seen that is non sorry, it is a CS stage with a source degeneration stage. So if you want to calculate the gain, it will be RD divided by, so that is the resistance of the source terminal. So the resistance of the source terminal is 2 2 RSS plus 1 by GM. 1 by GM is coming because the resistance seen here is 1 by GM approximately. That's why it is 1 by GM. Okay, so it will be GM RD divided by GM RSS into 2 plus 1. So if you take into account of the body effect, here you need to replace GM by GM plus GMB. So that's what it is. Okay, this is due to the body effect. And if you take GM denominator, it will be RD divided by 1 by GM plus of 2 times of RS. Okay. Okay. So so this is what it is. So if you take the ratio, the common mode rejection ratio, so this is AID divided by A common mode. Okay, So you can substitute here. AD is nothing but GM RD, that is the differential gain. So divided by this quantity, so that is uh, GM RD divided by 1 plus 2 times of GM plus GMB into RD. Okay, so this will cancel out. So all the denominator will come at the top. So the denominator here, it will come at the top. Okay. So this is much greater than 1. So that's how the design needs to be done. Okay. So now you can see here, because of the finite resistance, okay, so the rejection is not happening, but it is not as better as compared to the ideal current source. But definitely this is much better than what we had for the pseudo differential. Okay. In pseudo differential, common mode rejection ratio was 1, but here it is much more than 1. Okay. Yeah. So this is the summary. So in case of pseudo differential amplifier, so it is simple 2CS stage. So the differential gain is GMRD, and common mode gain will also come exactly the same. Because of that, the common mode rejection ratio is 1. Okay. So differential pair with the ideal current source. So here the RSS will be infinity. So the 2CS stages with the source degeneration resistance. So that resistance will be infinity if it is ideal current source. So because of that, the common mode gain is 0, because there is no change in current itself. Okay, so the differential gain will remain same. There is no change. So the common mode rejection ratio is infinity because of this. Okay. If it is a differential pair with the finite resistance, so this is the case in most of the circuits. We will have finite RSS. It will be very large, but it is a finite number. Okay. So in this case, the common mode gain is this one. So this we got it from the gain of the CS common gate when it is connected, when the resistance is connected to both drain and source. Okay, so you can go back to the equations. You will be able to derive this gain equation. Okay, so if you take the ratio, so the AD by A common mode, so we get some number which is much more than 1. Okay, so the only option to improve the common mode rejection ratio is making the better current source. So that is, the tail current source needs to be better, in the sense output resistance should be much higher. Okay. So GM basically depends on many other factors. So we need to look at the GM and we can size it accordingly, the diff pairs. Okay. Yeah. So there are few assignment questions. So this is the previous one is the homework assignment. That is the one. So this is the second one. So this is the third, and this is the fourth, fifth, sixth. Yeah, 6 assignment questions are there, guys. So you people needs to complete it. So we'll discuss this assignment questions in next class. Okay. So any questions you guys have right now?
No, sir. So one more thing is that lecture number 12th is not uploaded fully. Only 1 hour lecture I can see there. Last Sunday class.
Sorry. Sorry,
Lecture.
could you please repeat? I did not
That
get
lecture number
the
12.
comment.
It's
Yeah.
not. Yeah, lecture number 12 is not fully uploaded. I think it's partial. Only 1 hour class is there.
Okay. No. Like on Saturday, I think we did not have
The Sunday class I am talking
any
about.
class. Oh, even Sunday class is not uploaded completely.
Yes, yes.
Okay.
So it is
Okay, I will
uploaded
check
till
on that.
some issue
So
was
if
there, na, that
something is not recorded, okay. So I will go through the recording. If something is only that portion, okay. So in that way, it will everything will be a part of these recordings.
okay,
Okay.
okay.
Yeah. Okay.